So we're going to have this conversation be in two parts. The first part will be logistical concerns. So we will talk about the um, any any logistical concerns people have up to this point, what the style of the final is going to be, and then after that, we will have a content-based discussion. So to begin, does anyone so everyone's grades should be up to date, posted, and everything. Does anyone have any questions on um, on on what their grade is, on what they should expect? Anything, any past business, in other words. Will I be curving the course grade? Probably. Uh, but I don't know. I won't know by how much until we until everything's in. The extra credit quizzes are going to give you extra points on the final. I'm just going to straight up give you extra points on the final based on how many quizzes you did. Uh, it has not been applied yet. I have not curved anything yet. Uh, the final. Okay. We've got some questions going on here. So there, Jasmine's right. There will be about 5 extra credit points on the final um, due to attendance quizzes. There will be some sort of curve at the end, probably. Um, I mean, almost certainly. So the curve will only help, never hurt you. But I have to compare it to my expectation curve after all the final grades are in. The final exam is a week from today. Uh, it will begin at 8 a.m. sharp. The I think the technical time that UNLV says that we should start is 8:10, but that seems wild. Why 8:10? We'll just start at 8. You can have the extra 10 minutes. Um, you will have 3 hours. Right, so I expect the upload to be in by 11:10 a.m. I won't be here for all of that time because UNLV, in their infinite wisdom, has decided that you should only get 2 hours for final exams and so I have another final to give starting at 10. Yeah, you can't give any worthwhile final examination in just 2 hours. But since we're remote, there's no reason why we can't make it longer. Right? I already feel like 10 questions is too few, right? So the format, there will be 15 total questions. You'll pick 10. It'll be worth 70 points total. In other words, it's worth 2 exams. So Selena, I haven't taken any points off this semester for late uploads. 11:10 is a hard cutoff. Yeah, it won't accept anymore after 11:10. So our previous exams have been worth 34, 35 points. So this final exam is worth it's worth 2 of those. What this means is if you've done well on previous exams, if you've done well on 2 of the previous exams, then you can pick your 10 questions so that they are on the material that you've done well on. If you've done poorly on 2 exams, that means that the final is weighted enough so that you can stage a comeback. The final is not going to be based on previous tests per se, but previous tests did include what I thought were the best kind of questions. So, take that for what it's worth. I'll be grading 10 questions. So it's twice as many questions as previous exams, which is why it's worth twice as many points. Megan's got it. Answer 10 out of 15. You've got 3 hours, so twice as many questions, twice as much time. Hard cutoff at 11:10. I'll be around for 2 hours to answer questions. Questions will be about 7 points each. So there's plenty of room for partial credit. A little fear is motivational. Embrace it. Alternatively, go full Dune on it. I must not fear. Fear is the mind killer. Hey, for what it's worth, back when I was an undergrad many years ago, my first physics class, we had only 1 hour for the final because the professor didn't want to wait around any longer, and there were only 2 questions. Yeah, 2 question final is legitimately terrifying. So I'm trying not to put you through that. Casey, yes, I will be grading all the exams on my own in just 2 days. This class and my other lecture. Oh, well, yeah, I got an A in the class. That's why I kept. I mean, it was my destiny after all. There is no chance I will be teaching 152 next semester. Unfortunately. I mean, I shouldn't say no chance. There's always a chance that something happens, but I'm scheduled for only one lecture next semester, and it's a 182. In the summer, no idea. I'm actually applying for jobs in different states. Unfortunately, nobody ever gets a permanent job at the institution where they got their PhD. So you have to leave home and get a permanent position somewhere else. It's not a written rule, but it's a cultural rule. So, yeah, they literally do call it academic incest. So, yeah, that's the idea. You don't want to get any one institution too culturally locked, but on the other hand, moving is the least fun thing that anyone can do, right? Okay, so it sounds like we've exhausted questions about the final, which is great because it's a relatively straightforward thing. The I would like to talk about content after this. And for the bulk of our talk, I would like to present questions that you yourselves have come up with. So things that you aren't sure of. So I will do a little bit of a review. Um, sketch a toolbox from each chapter. But I would prefer to spend time on questions that have actually perplexed you all, rather than just covering what I think is, is nice or clever. So, uh, all right. So let's do a quick review, and then we will have a break so that you can all can prepare your thoughts, and then we will meet back, and we will cover any questions that you all have. So, chapter by chapter. Uh, in chapter 2, we studied one-dimensional kinematics, and we eventually expanded that study into two-dimensional kinematics using vectors. So our kinematic equations there is one involving position as a function of time. There's one with velocity as a function of time. And then there's a time-independent kinematic equation.
Professor Wolf, sorry to interrupt. Are we recording? Because I'm on my phone and I might get cut off, so I just want to be able to retrieve this later.
We are totally recording.
Thank you.
Let's take a moment and remember what Chapter 3 taught us about vectors. Right? We think of vectors, we should think of vectors as the hypotenuse of a right triangle. The length of that vector, which we denote with these vertical bars, can be had via the Pythagorean theorem. Similarly, the angle that the angle that the vector makes with the horizontal, or with any reference vector, can be had using an inverse trigonometric function. Right. Opposite over adjacent gives us the tangent. So arctangent of that ratio gives us the angle back. If we have the angle and the length, then we can get the legs using sines and cosines. So this is how we think about vectors. Okay. We often write vector components in angle bracket notation. And if we need to add two vectors, we can add their components. Now, that's a really good question, Casey. X and Y, right, are, like, which one we call X and which one we call Y is arbitrary, right? We have to define our coordinate system, and we have to specify which angle we're working with. So if we were using this angle beta up here, then AX would be a sine beta. So it is important to draw a picture, because, right, whether you're using sine or cosine, it depends not with whether you're using X or Y, but with the relative arrangement of directions and angles in the actual situation you're analyzing. That's a really good question, Casey. Okay. So that was chapters 2 and 3. The components of a vector can definitely be negative. right? So if we have a vector with negative components, that just means that if positive x is to the right, this -2 is to the left. To the left, up. And the vector is like that. Yeah. So negative signs are just indicators of direction. In what scenario will we need to use the square root? Yeah, anytime you want the magnitude of a vector, you have to use the Pythagorean theorem. That's the best way to get it. So the next thing I was going to say is if there's a negative sign out in front of a vector like this, that means the negative sign is applied to each of the components, which gives you a vector that is the same length but 180 degrees different. Did that answer your question, Jess? Okay. So the next thing that we went on to study is forces. And forces are just things that cause acceleration. And as a sub-note here, I will say that we know about normal force. We know about tension. We know about friction. And we know about centripetal force. Yeah, we're going to do problems after we do the run through. So we're going to do a brief run through, and then we will do problems after that. So this actually takes us up through chapter 6, which was the first exam. So this was all of the material on the first exam. We then went to talk about the effects of forces. So we started with the work-energy theorem, which states that a force applied over a distance does work, right? And here we have to specify that only the part of the force that is parallel to the work, or parallel to the displacement, does work, and work causes a change in energy. Again, as a subnote, we now know about kinetic energy. We know about gravitational potential energy. We know about elastic energy. And we know about rotational energy. Once we were done there, we went and we studied the impulse momentum theorem, where work involved a force being applied over a distance. Impulse involves a force being applied over a time. And an impulse causes a change in momentum. Elastic is the same as potential spring? Yes, that is correct.
Sorry to interrupt, but is that like W next to I a W or an omega?
That's an omega.
Okay, thanks.
Our definition of momentum is the product of mass and velocity, and we also distinguished between elastic and inelastic collisions. Right. And everyone remember what is the difference between an elastic and an inelastic collision? It is not deformation.
Conservation of energy?
That's right. Elastic collisions are ones where energy is also conserved. So momentum is always conserved, but under elastic collisions, mechanical energy is also conserved. When does something have both potential and kinetic energy? All the time. It just depends on where you define your origin. IMT means impulse momentum theorem.
Inelastic, the energy is not conserved, just momentum, right?
Right.
Thank you.
The last thing we studied for the second exam was rotation. We made heavy use of angular coordinates so that our linear coordinates divided by the radius of the circle we were dealing with gave us the value of our angular coordinate. We built up a rotational version of Newton's second law. right? With torque being equal to the perpendicular part of a force times a distance from the center of rotation. And I being the moment of inertia. So for a point, this is the mass of the whole object times the mass of the point times the square of the distance of that point from the axis of rotation. For other shapes, this has other forms, which you may need to look up. Wikipedia has an excellent list. We talked about rotational kinetic energy, but I already included that in the purple bit. We also built up an idea of angular momentum. And we dealt with this exactly the same way as we did with linear momentum. So momentum is conserved, and we examined torques changing angular momentum the same way that forces can change linear momentum. Okay, that was exam 2. Questions or comments?
I have a quick question. There was a problem in one of the exams where it was a torque, and what I did was I chose a pivot point that would give me one unknown rather than two, and
Yeah.
then solved for the force, and then just plugged it into F equals, oh, I don't know, the sum of forces equals 0, and I added them up or something like that. But I lost points. I'm unsure why. Is it because I did not explain why the forces summed up to 0?
Hold on to that thought, and when we do our problems in a few minutes, we will go over that.
Perfect, thank you.
Mm.
And can you just repeat C? That was the angular momentum, right?
Yes,
And the L stands for,
angular
Well-
momentum.
okay.
For reasons, historical reasons, we use capital L for angular momentum.
And then underneath it, that's torque again?
Torque times a change in time causes a change in angular momentum. So a torque applied for a time causes a change in angular momentum in the same way that a force applied for a time causes a change in linear momentum.
And then one last thing I wanted to ask you about linear and rotational motion.
Mhm.
There are a few equations that we can use. We can kind of use linear to go to rotation, but not others. And if I remember energy, we can't use the linear for rotational or something like that, right?
That's correct. These parts, the pink in A, that's how we translate between linear and rotational coordinates.
Thank you.
what are the equivalent of omega and alpha in linear coordinates?
V and A.
Okay.
Right. After the second exam, we started looking at fluids. So our first section was on fluid statics. So we learned about two big things in fluid statics. First, that the pressure of a fluid increases with depth. And this is for a non-flowing fluid. In fact, maybe I'll specify that. All right, so in a fluid system that is not flowing, pressure depends only on depth. And for something that is floating in a fluid, the amount of buoyant force that that object gets, is equal to the density of the fluid times gravity times the volume that is displaced. We added a little bit to this in chapter 12 with fluid dynamics. F is for fluid. We have Bernoulli's principle that in a fluid system that is flowing, the pressure plus the kinetic energy density plus the potential energy density is a constant. For pipes, the flow rate is the cross-sectional area of the pipe times the velocity of the fluid. And then lastly, flow rates are caused by changes in pressure. This is called Poiseuille's law.
May I ask a question?
Oh, yes, for sure.
For Bernoulli, I keep forgetting, has to do something with the depth, right? So if the depth's the same, we use Bernoulli. If it's not, we use Poiseuille or something like that.
No, the Poiseuille's and Bernoulli's talk about two very different processes. So Poiseuille's talks about the flow rate, so the amount of fluid moving through the pipe, and Bernoulli's talks about the energy of that fluid.
I see. Thank you. So remember the book mentioned something about if it's the same depth, then we have to use one equation. If not, we have to use another. But I'll bring up an example later.
Okay.
Is that V for fluid dynamics equation B, is that V volume?
That is velocity.
Oh, it's velocity. Okay, thanks.
That is a good question, though. I forgot to put the fancy hats on the V for volume up here. So thank you for reminding me. Also the cursive I? Where? What did I miss?
Sorry, I meant L.
Oh, yes, that's L. So. Yep. Cursive L's because otherwise they look like ones. And then the letter next to viscosity is the Greek letter eta. Which, yeah. Yeah, use of viscosity is the eta, length is the L. So we learned a few different things about heat to finish up exam 3. We refreshed ourselves on the ideal gas law, and we wrote it in the correct way that nature intended. We busted out the MCAT equation. So it takes heat to change the temperature of something. Heat can move via conduction. And it can also move via radiation. It can also move via convection, but we didn't actually mess with that. Every time you call the formula MCAT, the anxiety levels jump? No. I'm sure everybody feels entirely prepared for the MCAT at this point in their career.
for the last formula under heat, what are those what are those uh
This is so
um
the sigma is the Stefan Boltzmann constant, and the
okay.
epsilon is the emissivity,
Okay, thank you.
and then capital T is the temperature. Um, Last thing, there's also an energy. There's also a heat associated with phase changes. Where here this capital L stands for the latent heat. Okay. So this is everything that we studied up through the third exam. There are other formulas presented in the text, but they are algebraic manipulations of these basics. Questions or comments? Okay. Can we get a rundown of all the tables we need to look up values? Probably not. I mean that the internet exists, so the websites that I recommend if you need to look up something, you can check Wikipedia. Wikipedia has many lovely tables and lists, and you can also check Engineering Toolbox. Well, a lot of teachers are idiots. Wikipedia is the most beautiful thing that humanity's ever created. So, if anyone hates Wikipedia for some reason, then they need to get it. They need to start editing. Oh, you are right. There is one thing that we left off on heat. Thermal expansion. Okay. So that is the rundown that I had prepared for today. Uh, let's take 5 minutes, let's take 5 minutes, and we will come back, and we will talk about whatever problems or questions that you all have for the next couple of hours. All right. Where shall we begin? The difference between projectile motion and free fall problems, there is no difference. Projectile and free fall, they both use exactly the same kinematic equations. The only difference is which things we are taking to be zero initially. Did that answer your question at all, Jazz? So if we are looking at these kinematic equations up here, a projectile motion problem will use K1 and K2. A free fall problem will also use K1 and K2, except initial position is 0, or initial velocity is 0. That is the only difference. So if initial velocity is 0, you need to watch out for some keywords like if an object is said to be at rest, that's velocity 0. Or if an object is dropped rather than thrown, that's initial velocity equal to 0. Alright, so we want to go over exam 1 stuff. Got a request for question 5 from exam 1. Yeah, and this is actually a really good one. Reminds me why I liked it so much in the first place. So let's talk about what I am looking for in a solution. I don't care very much about the number you come up with at the end. It's just not very important. What's important is that you show me your thought process. Right? Because it is, I know all of these answers are online, and I know that you're probably referencing them during the test. That's fine. It is what it is. This is an online class. It's gonna happen. But if you just copy down the work that you found online, you are not going to get full points for it. And furthermore, you won't have gained anything. So, to that effect, there are 5 things that I expect to see in your solutions. And the first thing I expect to see is a picture. It has been said that most of the errors that students make in intro physics are actually reading errors. A picture helps you kind of bring together all of the elements in the words of the problems, but bring it together in a concrete way. So this is how you demonstrate that you have read the question correctly. It is almost always necessary to specify the coordinates that you're going to be working with in your solution. I need to know which direction is positive and which direction is negative at the very least. And in two-dimensional problems, I need to know what you consider the x direction and what you consider the y direction. It is very important also, if you have vector quantities, break them down along the x and y that you just specified. If it's not a two-dimensional problem, you at least need to collect the information that you're going to be using in your solution in one place. And then we do physics. And by say we do physics, I mean we take a look and we see which of these principles is going to allow us to chip away at the problem. Like which one of these includes what we want. And now these things that I've listed here, these equations, these are all generally true, right? These are correct descriptions of the natural world in a general sense. Any other equation that you might pull out of your book or from the internet is a special case. It's true sometimes. Where did my layer go? Seriously? There it is. So you need to either start from something that's generally true or spend a while explaining why the special case equation that you're pulling out applies to this case. A frequent source of lost points is what I call magic equation syndrome. Where it looks like you pulled an equation from the book or the internet that had the right variables in it, but you didn't know, like you didn't give any indication that you knew what it meant or where it came from. And yeah, you lose points for that. Because it's your problem-solving process that is not only the most important thing to me, but is the reason that you're studying physics in the first place. And then the last and most boring step is actually doing the algebra. Okay. So, we have a football quarterback that's moving straight backward. And then throwing a pass. So the quarterback themselves is moving to the left, right? So we'll say that downfield is the positive direction, up is the positive direction. And so we're throwing this ball. It's thrown at an angle of 35 degrees above the horizontal. And it's going to be caught by another player at the same height at which it was thrown. There's a 21 meter separation between these two players. So our questions here are: what is the initial speed? And how long does this pass take? So we are going to use K1 for short, Jolene. So let's write that down. We'll write that down. So we are going to be using So the things that we are going to be interested in are position, velocity, acceleration, time. Two of those things we already know we don't know. But let's do our best at writing down the rest of those things. So our initial position, right? So the moment the ball leaves the quarterback's hands, let's call that the origin. The final position right? So we're going through what we suspect we're going to need because of the equation we expect we're going to use. Right? Our final position will be 21 meters downfield, but still a height of 0. Our acceleration is going to be nothing in the x direction, and it's going to be minus 10 in the y direction. Our initial velocity, we don't know the speed of it, but we do know that the angle is 35 degrees. All right. And we note if we're analyzing the motion of the ball, which is what we're doing, do we care about the motion of the quarterback? Right? Does the motion of the quarterback matter? No. Motion of the quarterback doesn't matter. Right? We didn't know that at first, right? So when we were drawing our picture, we were just drawing the best picture we could. It's only after we started really thinking about it that we're like, you know what? We don't actually need that. So, any advice on not getting tricked by red herrings? The only way to do that is to realize is to you can't look for equations that have all of the information in them, right? You have to look over your tools and look for ones that give you what you want, and then take stock of what you need to get there. All right. So in all of our information that we've written down here, how many unknowns do we have? How many things do we not know? Yeah, we don't know two things. We don't know the speed, we don't know the time. We do know theta. It's 35 degrees. But yeah, two things we don't know. If we have two things we don't know, how many equations do we have to write down in order to solve? Also two. Yep. Two equations will let you solve for two unknowns. So here, since we have a two-dimensional problem, the kind of natural equations to write down is just take the x parts of the movement and the y parts of the movement. So in the x direction, we have x equals x naught plus v naught x t plus 1/2 ax t squared. Yep, our recording is good. In the x direction, our initial position is 0. Our acceleration in the x direction also 0. So we just have x equals initial velocity times time. In the y direction, so y equals y naught plus v naught yt plus 1/2 ay t squared. Here, the initial and final y positions are both 0, right? Because we just wrote that down on the left in blue. So boop, boop, those are both 0. So we have, and we know what the acceleration is. It's g, right? So maybe, okay, this is actually g. Okay. Now, between the two of them, these equations will give us the capability of solving for everything that we want. So one strategy is to take the x direction and say, well, actually, that means that the time is going to equal x over v naught x. Why is the 1/2 negative? Because the acceleration over here is negative. Right, so I just brought the negative sign out in front of the whole term. The x is 21, but I'm not going to plug in any numbers yet. I am going to plug in this expression for t down here. And I'm going to note that v naught x is the same as v naught times cosine of the angle. And similarly, let's move this over. This v naught y, we can write that as v naught sine theta. So there's a reason that I'm not plugging anything in yet, and it's because I want to demonstrate something. So we have some cancellation going on. We can divide both sides by x as well. And we can rearrange a little bit, take this negative term, move it to the left-hand side. Or in other words, we could write this as x equals sine theta cosine theta 2 v naught squared over g. Using a little trigonometric manipulation, we can actually reduce that numerator to sine of 2 theta. Now, very many of you on this first exam started here. And you all lost points for it. Why would you lose points for that? What's missing if you just start at this pink bracketed thing? How you derived it, sure. Yeah, and the conditions under which that formula is true. Right? So if you start with things that are always true, like this kinematic here, and you manipulate it based on the values that you've actually got in this situation, then your math itself is the argument for why the equation you come up with is correct. If you start with something like the pink bracketed expression, and you go from there, right? You're completely, you're not giving any sense that you're aware that this pink bracketed thing is not always correct. Right? So the conditions for this pink bracketed thing, let's just take a look back. Right? The things that we need to be true are final height equals initial height. We need AX to be equal to 0. We need initial X position to be equal to 0. And we need AY to be equal to G. Minus G. Yep. And if you are thorough about your answer and you do the blue part and the brown part, then it's very clear that you know what you're doing. If you start at the pink bracketed part, then there's no indication that you know what it's about. It looks like you just pulled it off of Chegg. So even if it's not true, even if you didn't just pull it off of Chegg, that's what it looks like, right? So I need to see your reasoning. Does everyone know what I mean there? And since here we are using degrees as the measurement of our angle, we need to make sure that our calculators are in degrees mode. Oh, I used a trigonometric identity. Sine of 2 theta equals 2 sine theta cosine theta. Okay. Questions or comments on this problem? If you're so in this kinematic section, we are frequently speaking in degrees, right? So 70 degrees, 35 degrees. However, when in the later chapters, when we talk about rotation, we will always be talking about it in terms of radians. Right? So degrees are the measurement that like sometimes works, and it's traditional. So sometimes you can get away with talking in degrees. You can always use radians instead. In all of the rotation stuff. All of the rotation stuff used radians. Anytime when we had an omega, right? Omega is always in units of radians per second. Okay. Do we have more? Who has another problem that we want to look at? We've got a request for exam 3, question 3. So, exam 3, question 3, was a tough one for basically everyone. And the problems with it happened almost immediately. And like I said, most physics mistakes are actually reading mistakes, and this was definitely one of them. So if we have a pipe system like so. The output to this pump is somewhere off to the right. And then we also have, so we'll call this maybe position A, B, C, D. So the number one error here is people said that the pressure at A is equal to 3 atmospheres. Right? The question states that the output pressure is 3 atmospheres. So the pressure at D is 3 atmospheres. We are also told the flow rate is equal to 0.5 liter per second. Liters are not a good unit for us to be using, though. What else do we have here? Right, so we want to know the pressure at points B and C. Right? And we have a connected system of pipes that is moving, which means we know we're going to use Bernoulli's equation, or Bernoulli's principle. So the pressure plus the kinetic energy density plus the potential energy density is going to be constant throughout this system of pipes. Okay. Are we okay so far? Another issue that people made is they just said with no explanation that this term was 0. but there was no kinetic energy density. The problem with that is the water is flowing through these pipes. So if it is flowing, the velocity is not zero, and it does have kinetic energy. So instead, the better way of doing this would be to just try and find out what the velocity is. And we know that through any connected series of pipes, the flow rate is equal to the cross-sectional area times the velocity. And we've been given the information to calculate the cross-sectional area everywhere here. Like we know that the hose has a 4 centimeter inside diameter. For example, from A to B. And we know what the flow rate is. The flow rate is the same everywhere in the pipes, as it must be, because what goes in must come out, and the rate at which it goes in must equal the rate at which it comes out. So the velocity between points A and B has to equal the flow rate for the system divided by the cross-sectional area of the pipe from A to B. Where this 0.02 comes from taking the diameter and dividing it by 2 to get the radius. Is everyone good with this so far? We're okay so far? Okay. So that has to be the velocity from A to B. We can also figure out what the velocity must be at point C. The velocity at point C has to be the flow rate divided by the area of the pipe at C. Where again, the diameter which is given is 8 centimeters, so if we want the radius in order to calculate the area, we have to divide the diameter in half. So this bit right here, I want to make the point, this pressure, whether pressure at A or pressure at D equals 3 atmospheres, I didn't take off for either interpretation of that. Right? Because I think the question has sufficient ambiguity that either one of those is a reasonable interpretation. But this velocity stuff here, almost nobody considered the velocity. So that is what I took off points for. So Jeanlin, the book does not say that depth has to be constant, right? Depth is because the Bernoulli's principle is for pipes, right? So there isn't depth to be considered here, right? We don't have a column of water that's pressing down on the water in the pipes because they're in pipes. Does that make sense? So Bernoulli's principle applies whenever you have a flowing fluid. In this class, we only considered fluids which were encapsulated in pipes, which means they basically don't have a depth. Like, sure, you could calculate a small difference in pressure from the top of the pipe to the bottom of the pipe. So technically, I guess, we're calculating the pressure at the top of the pipe. But the difference is so small over a distance of 4 centimeters that we end up disregarding it. When we're talking about level flow and constant depth, usually we're talking about that for unconstrained fluids. Like if we wanted to analyze currents in an ocean or airflow over a wing, that's when that would be important. But we're not considering anything that complicated in this class. It'll only be pipes. Okay. There are at least 2 ways to proceed with this problem from this point, after we've calculated these velocities. The first way, and which maybe so it depends on whether you took the output pressure to mean output of the entire system or output of the pond that you were sucking out of your basement. if you considered the 3 atmospheres to be over here. Then the best way to go about this is to apply Bernoulli's principle from D to C and then C to B, working backwards. You could, if you took the 3 atmospheres to be here, now you can apply Bernoulli's principle from A to B and then B to C, and get your answers that way. Either of those would have been fine. Right? I was prepared to give full points on either of those. After thinking about it, I think the way that I ended up going over it the first time is probably the least intuitive way, or the least efficient way. So, but yeah, if 3 atmospheres is here, then we apply Bernoulli's at D and compare that to Bernoulli's at C, set them equal to each other, solve for pressure. And then we can also compare C to B. So let's run through that real quick. So we could say the pressure at D plus the flow at D, the kinetic energy density, actually no, this doesn't work. I lost my train of thought. And Jolene is leaving. She's the one that asked one of the question in the first place. Yep, I'll see you next week, Jolene. We can make use of Pucell's law here. The flow rate between C and D, we know it's half a liter per second, and that's going to be due to the pressure difference. And this R, we have everything we need to go in here. Well, actually, I guess we don't need it. I should have had another cup of coffee on my break. I'm losing my train of thought. I had this all diagrammed out because I knew someone was going to ask about it today, and then I didn't save it. Start from the other end. So in fact, let's start from the other end because everybody, I think, made the assumption that the 3 atmospheres was over here. If this is the case, then the pressure in at A plus the flow rate All right. Now, at this point, what can we say about the flow rate at A, or sorry, the velocity at A versus the velocity at B? Right, because over here we calculated, right, this velocity for an in-between. Yeah, it's the same because the pipe hasn't constricted yet. And the pressure here, we need to be careful, and this happened to a few people. We say 3 atmospheres, but the units of these terms here are in pascals. So even though we say 3 atmospheres, what we really need is 303,000 pascals. What is the height of the system? What is the height at point A? Yeah. And the height at B, that's our 3 meters. Okay. Is anyone... I only see Jasmine talking in the chat now. Does that mean that everyone else is perfectly fine with this problem? What does that mean? So, Jillian, can you be more specific? Okay. So remember, so here we get something like PB equals 273,000. Some of you did in fact come up with this number on the exam. But nobody who came up with this number also considered the velocity in any way. Right? So when I said earlier, I don't actually care very much about the number you get at the end. Like that's legit. You get the right number for the wrong reason, and you get no points for that. Right? So if you get the right answer for B on accident, because you neglected the velocity of the pipe, right? Then, right, that's an issue. Because the final number, I don't find very interesting. It's your thought process I find interesting. Questions? Okay.
Dr. Wolves is excuse me, is that for B? Is that the pressure? So sorry, I had to drive my mom to surgery, so I'm just joining a few minutes late.
Yeah, so that's our number for the pressure at B.
At B. What was the pressure for A?
So in this situation, right, we were analyzing this because the majority of students read the problem and assumed that this 3 atmospheres was talking about the pressure at A. So I was actually analyzing it based on that assumption. So at A, it's 3 atmospheres. At B, it's less because you exchange some of that pressure for height.
Thank you.
Chad, did you mention that you had another problem that you wanted to look at? Okay. I don't think I mentioned. I actually am pretty pleased with how people did on exam 3. Like the average score was noticeably higher than the first 2 exams. Alright, so what else do we want to talk about in the time that we've got? Chapter 7, question 5. Alright. Dude pushing a box up a ramp. Truly a modern day Sisyphus. Okay. There's some things missing from this diagram, wouldn't you say? Let's fill in the gaps. What should our coordinates look like in this problem? Up and to the right is positive. Up is positive. Okay, let's do both. We'll start off also. This is we're going 4 meters up. So we're being asked about work. So we know that we're going to be using the work energy theorem. So a force applied for a distance causes work which in turn causes a change in energy. All right. So if we're considering I think since we're going up a ramp, the best coordinates to consider are probably something like this. So the work done by the man on the box is going to just be equal to the force he applies on the box times the distance. Now, it's harder to think about the forces that the man is exerting on himself. So for the first part, considering the work on the box, we used this part of the equation of the work energy theorem. When considering the work the man does on himself, I think it's easier to consider this bit. Right? What change in energy does the man experience as he goes up the ramp? Does he exchange a change in kinetic energy? Because be careful to say that it's a constant speed. So there's no change in velocity. Potential, yeah. So work of the man on himself will be equal to the change in energy experienced by the man, which is going to be mg times change in height. Right? And how much height change did our person experience? He went 4 meters into the air. 4 sine 20 into the air. That's right. So for his own part, he experienced a change in energy of 1,162 joules. So that must have been the work, right? The work that he did to cause that change in energy. So in total, we have 2,000 joules of energy exerted on the box and 1,100 joules of energy exerted on the person, or work exerted on the person, for a total of 3,162 joules. Does that sound right to everybody? What else should we look at today? All right. Well, if no one has any other questions today, that's okay. I know that you will all be going through more problems in the coming week, and I will still be holding office hours next Wednesday at the usual time, so that you can come with your questions then if you think of any that you that didn't occur to you now. Words of encouragement. You have seen everything this class has to offer. There will be nothing new on the final. And yeah, so just don't give yourself a heart attack over this, right? Like, do some problems, right? Even do a lot of problems. But yeah, but there's not going to be any surprises or gotchas on the final. It's going to be old hat. Yeah, if you review the old exam questions, that's a good place to start too. After all, the exam questions I thought were good enough to give to you once, so that's a pretty good indication of what I think is important. But I think you should also do problems from each chapter, especially if there's problems that you've left undone over the course of the semester. You did literally all of them. Well, it showed in your exam work. I believe there's going to be feedback forms on Web Campus. I would ask you all to fill them out and give me an idea of what I can improve for next time, and also let the department know that I was doing an okay job, if I was doing an okay job. Yeah, I mean the exam's going to be the same as the final is going to be the same as the other exams. They're going to be in order. So it'll go in order from chapter 2 to chapter 15. And there will still be basically book questions. So if you have done all of the book questions, then you have almost certainly seen the questions that are going to be on the final already.